how our studies barely touch the surface of black holes. A black hole is an extraordinarily dense object in space from which no light can escape. While black holes seem enigmatic and exotic, they are also a vital consequence of how gravity works. When a large amount of mass is squeezed into a tiny enough space, the resulting object tears the very fabric of space and time, resulting in what is known as a singularity. The gravity of a black hole is so strong that it may suck in neighboring matter and devour it. But is that all? There is a lot we don't know about black holes. So how does our research barely scratch the surface of black holes? They are so powerful not because of their mass but because of their size. First, a little introduction to black holes, okay? Stay with me. In the center of a big star, a black hole can develop most often. As a result of a fuel shortage, the core disintegrates. As a result, the star's outer layers explode in a supernova, creating a shockwave. The star's core therefore disintegrates while the rest of it erupts into space. Gravity increases when the core disintegrates. The escape velocity eventually reaches the speed of light at the surface of the collapsing core if the core is larger enough, about 3 times the mass of the Sun. This happens when the gravity becomes sufficiently powerful. That implies that nothing, not even light, can defy this object's gravitational pull. It is hence black. The event horizon is the area around the black hole where the escape velocity is equal to the speed of light. Everything what occurs inside of it remains unseen forever. So now you're aware of what one is and how it develops. I can now explain why their gravity is so powerful, but what do you think? You have it then. The mass is significant for sure, but often it's the small things that matter most. They're indefinitely little. They are little indeed, but how tiny are they? When I was working at my former employment, we had a lively conversation about what exactly we meant when we said black hole. We were referring to the event horizon around the black hole, or the actual entity that collapses to a mathematical point. My employer asserted that the item was the event horizon, but I disagreed. I acknowledged that she had a point and took care to express myself clearly when I contrasted the event horizon with the black hole itself in my writing. Even while the event horizon has a fixed size, as I mentioned before, to the collapsing core its clock keeps running. Thus it perceives itself collapsing all the way down to a point. How does the core fare? What was the actual collapsing mass? We'll never be able to be sure out here. We are unable to see inside and it is not going to transmit any information. However, our arithmetic under these circumstances is rather sound, and we can at least apply it to the collapsing core, even when it is smaller than the event horizon. As it keeps collapsing, the gravity gets stronger. Smaller, and when I was a child, I remember reading that it eventually collapses to a geometric dot, a thing with no dimensions at all. As you might guess, that it truly bothered me, as it should, because it is incorrect. The center of the exploding star will eventually be smaller than an atom, a nucleus, or an electron. It will ultimately shrink to a size known as the Planck length, a measurement so tiny that quantum physics will have complete control over it. If an item shrinks below the Planck length, we simply cannot know too much about it with any confidence. This is a form of quantum size limit. The mechanics are complex, but when the collapsing core reaches this magnitude, we wouldn't be able to determine its true size even if we could somehow penetrate the event horizon. In reality, at this type of scale, the phrase actual size is meaningless. You may as well claim that the phrase has no meaning if the universe itself forbids you from measuring it. What size is a Planck length exactly? Tiny. Between 10 to the power of 35 meters, that is 100 quintillion times smaller than a proton. Therefore, you may be all nerdy and technical and respond, not really, but meh. If someone asserts that a black hole has no size, near enough. They're spherical, they also most certainly do not resemble a funnel. A weighed object's mass and your proximity to it both affect how much gravity you experience. This implies that everyone at a specific distance from a larger object, such as a million kilometers, would experience the same amount of gravity from it. Everybody on the surface of the sphere would also experience the same gravitational pull from the item in its center if it were defined as being that far away. The event horizon of a black hole is really a sphere that surrounds the black hole, since the size of an event horizon is dependent on gravity. If you were able to see the event horizon from the outside, it would appear to be a completely black sphere. Some people imagine black holes to be formed like circles or worse, like funnels. The space is like a bedsheet, they argue, and objects with mass bend space in the same way as a huge item like a bowling ball, for example, will warp a bedsheet, which leads to the misperception that gravity bends space or the funnel effect. This explanation may leave some people puzzled regarding the precise form of a black hole event horizon, since space is not 2D. Rather, it is 3D, or even 4D if you take time into account. Kids have questioned me about what happens if you approach a black hole from below. They occasionally fail to understand that black holes are spheres with no underside. The funnel narrative is to blame. We are constrained by this example since it is the finest I have come across. Use it carefully. The black hole spins. Black holes can spin, which is a kind of a strange idea. When the core of a star collapses, the star's spin speeds up dramatically. The usual analogy is that of an ice skater who brings in his arms, increasing his rotation rate. The star rotates more quickly as the size of its core decreases. The matter is compressed to become a neutron star, which is a ball of neutrons a few kilometers in diameter, if it lacks sufficient mass to form a black hole. These items, of which we have found hundreds, have a propensity for spinning hundreds of times each second. A black hole operates in a similar manner. The stuff is spinning even as it gets smaller and smaller until it crosses the event horizon and is permanently lost to the outside universe. If you're attempting to determine what happens to the matter as it enters the event horizon, this is not quite apparent what it signifies. Is it prevented from completely falling to the Planck length by centrifugal force? The math is difficult but not impossible, and it suggests that matter entering the event horizon will collide with matter already there that is trying to fall further, but is unable to do so due to rotation. This results in a huge pileup and some spectacular fireworks that we'll never be able to see because the event horizon is on the other side of infinity. Bummer. Not all black holes are dark. Black holes can actually be deadly from a great distance. Rarely, if ever, would matter going into a black hole just fall in and vanish. It will encircle the black hole if it moves slightly in a sideways direction. All of this waste might accumulate around the opening as additional material falls in. This matter will form a circle of material whirling frantically about the hole due to the behavior of rotating the objects. Because the gravity of the hole varies so quickly with distance, things close to the hole will be circling considerably faster than stuff farther away. This material really rubs against one another, creating heat as a result of friction. This material has an extreme temperature range, millions of degrees hot. This means that near the black hole, this stuff can be significantly luminous. Hot matter shines with great brightness. Even worse, two energy beams that pierce the disk's poles can be focused by magnetic and other forces. The beams are visible for millions or possibly billions of light years after they begin just beyond the black hole. They are bright, in fact. Black holes that are consuming matter in this way have the potential to shine so brightly that they become the stars of the cosmos that radiate light continually. These black holes are active, as we say. The stuff becomes so heated just before it takes the last plunge that it may ferociously release X-rays, high-energy types of light, as if black holes weren't already frightening enough. And the beams can emit even higher energy light than that. Therefore, even if you leave your spacecraft well outside the event horizon of a black hole, if something else falls in and is destroyed, you will still receive the equivalent of 1 billion dental checkups worth of radiation as a price. Black holes are harmful, as I may have already stated. It's best to avoid them. What else can I say? Black holes are strange. Fortunately, there was obviously a lot more that could be said about them. Wormholes, how about them? What about their formation? Regarding Hawking radiation, do black holes ever completely vanish? There is a great deal that we do not yet understand. But this all for now. So what are your opinions on black holes?